Alrighty, number 24. Rectangular loop of wire with dimensions 1.5 centimeters by 8 centimeters and resistance R equals 6.6 ohms is being pulled to the right out of a region of uniform magnetic field. Magnetic field has a magnitude B equals 2.4 teslas and is directed into the plane at the instant when the speed of the loop is 3 meters per second and it is still partially in the field region. What force, magnitude, and direction does the magnetic field exert on the loop? Okay, so first of all, we are pulling this little loopy out of the field, which means we are changing the flux, so we are inducing a current in this loopity. So the force that this loopity feels is because of that current, so let's find that first. So if we start with a nice little loopity with a couple of dudes, and we pull it out of the field a little bit, our flux is going to decrease. So in order to keep everything happy, we are going to induce a field to get back to the original. So we are going to induce a field that way, so that this plus this is what we started with. So if we're inducing a field into the page, our current is going that way, and our EMF is minus d flux dt. So it's going to be minus d dt of our flux, which is B times the area, which is length times width. We're going to call this the length, and then the width the short side. Okay, so time derivative of this, our B is constant, so we can pull that out. Our W is going to be constant, so we can pull that out. The length of the rectangle that is inside the field is what's going to be changing. So we have dl dt. Now the length of this dude, the length of the wire that is inside the field here, we can write as distance equals velocity times time. That's going to be minus bw d by dt velocity times time. So if we take the derivative of that, we're just left with the velocity. So our induced EMF is B times the width times the speed that we're pulling it out of the thingamadoodle. So from V equals IR, the current that gets induced in that loop is going to be our EMF divided by R, which is going to be our BWV over R. I'm not going to worry about the minus sign because we already figured out the direction of our current from our pictures. So I'm just going to ignore that. So the current is BWV over R. Now the force that our beautiful loop-a-doop is going to feel is going to be from our F equals IDL or IL cross B. So if we look at our pieces of wire, our current is flowing this way. Doop, 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 doop. So this one is out of the loop, so he's not going to feel the force. This one, I have I, DL, cross B is going to feel a force down. IDL, B is going to feel a force up. So this one and this one are going to cancel each other out. So the only one that's going to contribute is this wire. So our IL, B, it's going to feel a force to the left. So our I is BWV over R. Our L here is W, and then times B. So if we simplify that together, we have B squared, W squared, V over R. All right. So Let's punch this into our handy dandy calculator. So our B was 2.4 squared times our width, which was 1.5 centimeters, so 0.015 meters, times our V, which was 3, and divided by R, which was our 0.6. So the force that our loop is going to feel is 6.48 millinewtons to the left. All